Hello, this is video 53. In this video I just want to do one more example that has to do with collisions, but it also brings in energy as well from the previous chapter. So this is called the ballistic pendulum. It's a very common problem. So people actually do a lab with it if they have the equipment. A projectile of mass 50 grams enters a pendulum with block mass equals 1 kilogram, which swings up to a height h equals 10 centimeters, where it momentarily stops as shown in the figure. Find the initial speed of the bullet. So you can see what's happening here. You have a bullet that is going into a block, it becomes embedded in there, and then the block and bullet move up together to a certain final height. So you can imagine the faster that the bullet is shot into the block, the higher that they're going to go. So this is a two-part problem. You can see that there's a collision over here, but then as soon as the bullet becomes embedded into the block, they both rise. That's conservation of energy. So we really have to separate and look at the two parts separately. So let me go ahead and draw a picture first for the collision. Remember, when you're doing collisions, you care about the initial part and the final part. What happens right before the collision and what happens right after the collision. So right before the collision, you have the bullet, which I can actually draw it right here. The bullet is just about to enter the block, and right after the collision, the bullet has become embedded into the block. The block has not started moving yet. That's a common misconception. So the block is still, well, the block is just going to start moving, but it still hasn't gained any height yet. Alright, so this is the initial condition, this is the final condition. So let's say that M is our bullet and M1, and M2 is our block. So M1 has a mass of 50 grams, 0.05 kilograms. M2 is the block, which has a mass of 1 kilogram. And then we need to define three velocities because they stick together. So V1 initial, V2 initial, and V final. We don't have to worry about the x and y directions here because the collision is just in one dimension. So V1 initial is actually what we're looking for, the initial speed of the bullet. V2 initial, the block was originally at rest right before the collision, so it's 0. Now VF is the final speed immediately after the collision. We don't know what it is. So we have two unknowns here. We can write down conservation of momentum, M1 V1 initial plus M2 V2 initial equals M1 plus M2 times V final. We can cross out V2 initial, that whole term, because that's 0. But we have two unknowns. We don't know V1 initial, we don't know VF. So what we need to do is we need to take a break and then look at the second part of the problem where this happens immediately after the collision. The bullet has just been embedded into the block, and then the bullet and block together rise to a certain height. So this is conservation of energy. So they have some initial speed here, and then when they get to the maximum height, do you know what the final speed is? It's going to be 0 because they're not going any higher. They stop right there. And we have the height that it gets to. So conservation of energy, we can go ahead and write it down. We have M 1/2 mv squared initial plus mgy initial equals 1/2 mv final squared plus mgy final. Now the mass here, M, represents the mass of the block and the bullet combined, but it doesn't even matter because it's in every term, it cancels out. And with conservation of energy problems, we have to define our 0 level. The lowest point that we care about is going to be right here, y equals 0, y initial. So we know we have no initial gravitational potential energy. We can cross out that whole term. We know we stop. We have no final kinetic energy. So we're left with 1/2 v initial squared equals gy final. And the y final is the given height h, which was 10 centimeters. So 0.1 meters. So here we only have one unknown, which is v initial. So we can solve for v initial. We can multiply both sides by 2 and then take the square root. So the square root of 2gyf, and we're going to get 1.4 meters per second, where I just plugged in the square root of 2 times 9.8 times 0.1 meters here. So now what do we do? Well, we just found what was v initial, but remember, v initial was the speed immediately, and I have to write this down because a lot of students get confused, immediately after the collision. Well, now let's go back to our collision. You see how this scenario right here was also immediately after the collision? So that means that what we called v initial down here, since it was immediately after the collision, is the same thing that we're calling v final here. They're the exact same thing. So v final in this case is the 1.4 that we just found. So now we can solve for v1 initial, which is the initial speed of the bullet here, which is going to be m1 plus m2 times vf times the 1.4 over m1. So let's plug in our masses, plug in the 1.4, and we're going to get a final answer of 29.4 meters per second. So that makes sense. The bullet has to be shot pretty quickly in order to be able to embed into the block and then rise up to a certain height. So this is just an extra example I wanted to do because it does combine momentum and energy, so it's a good review of the two topics.